Hi, everyone. Thank you so much for joining us for the next entry in the PCI SIG webinar series. We'll get started in just a few moments here. Thank you. Hi, everyone. Thank you so much for joining us for adoption of PCIe technology and IoT applications as part of the PCI SIG webinar series. I'd like to take a moment here to introduce our speakers for today. We have Debendra Das Sharma, who is an Intel Fellow at Intel and a PCI SIG board member, as well as the chair of the Philogical Work Group. We also have Anil Kumar, who is a principal engineer in the client computing group at Intel as well. With that, I'll go ahead and pass it off to the presenters, but please do feel free to submit questions as they are speaking as well. We'll take time for Q&A at the end.
Greetings. My name is Devendra Das Sarma. Here is the agenda for today. We will start with an introduction to the different segments that we collectively call Internet of Things or IoT for short. Then we will discuss about PCI SIG and the evolution of PCI Express technology. Next, we will delve into the application of PCI Express technology to the various IoT segments, edge computing, test equipment, industrial and embedded PCs, and automotive. Finally, we will conclude and then take your questions. IoT is one of the most diverse segments in the compute continuum that touches all aspects of our lives. As we will see, IoT systems are everywhere, deployed in tens of billions of devices from agriculture to home appliances to industry automation to automobiles. So the contribution of this segment to human endeavor is tremendous. It has and continues to transform the way we live and we work. IoT is deployed in the field of medicine, it's saving lives. It's in all of our gadgets and home appliances, which is fundamental to the quality of modern life that we are all used to. We deploy it in agriculture to monitor conditions and take corrective actions to improve crop yield. We see it increasingly deployed in surveillance for public safety. We see it in factories to optimize productivity, cost effectiveness, and efficiency. We are also deploying it in things like energy and utilities, monitoring our flora and fauna health through drones and satellites. Basically, everything we need to do to protect our planet for our future generations to enjoy and thrive. In short, it is ubiquitous. Most of it we probably do not notice and take for granted. Continuing on the theme of IoT touching every aspect of our lives, IoT represents a wide range of vertical markets spanning retail, manufacturing, smart cities, energy, utilities, transportation, public sector, education, hospitality, health and life sciences, automotive, banking, gaming, entertainment, touching practically every aspect of human lives in this planet and beyond. As we have seen, IoT represents a wide range of diverse systems. These span edge, gateway, data acquisition devices, automotive, modular computers, industrial PC, and are deployed in tens of billions of connected devices around the globe. This is natural as digitization is seeing tremendous growth and driving businesses to modernize, as illustrated by a few statistics here. The amount of growth is around 200% for information-based products and services. It's projected that we will have 80 zettabytes of data by 2025, which are generated by 40 plus billion connected IoT devices. More than 60% of developers deem IoT is very important to their digital strategies. We expect more than 55% of all data forecast to be generated by IoT by the year 2025. Half of this data will be created and processed outside the data center or the cloud, in other words, in the IoT space by 2022. More than 40% of AI tasks are going to take place in the edge devices by 2023. It's a 300 plus billion-dollar annual B2B revenue opportunity that all the companies are interested in leveraging. One of the characteristics of the emerging edge and IoT market is the exponential growth in the data. Businesses need to constantly transform to keep up with these challenges. We expect 70% of enterprises will be running varying levels of data processing at the IoT edge by 2023. 70% of IoT deployment will include some kind of AI solutions for autonomous or edge decision making. 65% of organizations will aggressively modernize their legacy systems to handle these challenges. 60% of organizations will have invested in automation, orchestration, and development lifecycle management of cloud native applications and platform by 2022. Half of the large global enterprises will rely on third-party service providers for help with containers, open source, cloud native adoption, and development by 2024. So what this means is IoT is moving into a space of an open ecosystem. It's going to deal with tremendous amount of data. Most of this data will be processed, stored, and analyzed at the edge to help deliver better latency, conserve network bandwidth, and improve reliability, security, and privacy. As the data growth explodes, high bandwidth IO capabilities along with AI will become necessary to transport and to transform this data into actionable information and valuable insights. Before we delve into the role of PCI Express technology and the role it plays as the primary IO interconnect in the IoT space, let's look at some of the capabilities that are offered by PCI Express. PCI SIG is an open industry consortium founded in 1992. Currently, it has 830 plus member companies worldwide. Uh, it is responsible for developing PCI Express specification, doing the compliance and interoperability program. PCI Express is ubiquitous across multiple segments, as you can see, of course, IoT being there. It has 9 board of director members that gets elected annually, and you can see the list there. PCI Express is a layered architecture with a proven track record of full backward compatibility. A layered architecture helps with the technology transitions. We have a well-defined software mechanism. An architected configuration register mechanism helps with device discovery in the system. PCI driver interfaces with OS, VMM that abstracts the underlying hardware, and it has evolved in a backward compatible manner since the bus-based PCI days. At a hardware level, we have transaction, data link, logical file, and electrical layers. Each layer has a set of architected configuration register that also evolves in a backward compatible manner. The transaction layer is based on split transaction packet-based protocol, which deploys credit-based flow control. We have virtual channels to guarantee quality of services. The data link layer provides reliable data transport services. It deploys things like cyclic redundancy check on packets, does retry at a link layer level, has an ACK protocol. Effectively, anything going on that PCI Express link is guaranteed at the hardware level to be delivered to the link partner. The logical file layer is responsible for doing things like encoding. It does initialization. It does maintenance of the link. The electrical layer is responsible for dealing with the signaling, speeds and feeds, all of those. Now we got multiple form factors which fall in the realm of mechanical, and these are market segment specific form factors. They are both evolutionary as well as revolutionary in nature. This kind of layering approach helps PCI Express maintain backward compatibility with ease. When we make speed changes, we keep the other layers mostly intact. Similarly, when we make transaction layer enhancements, they are applicable in irrespective of the speed. So some examples of transaction layer enhancements include things that we have done to support IoT segments like precision time measurements, IO virtualization, transaction processing hints for efficient data flow between CPUs and accelerators so that they can work across all the speeds and feeds. PCI Express technology has a long track record of being implemented in high volume manufacturing products like PCs that are cost focused and reliable. Even though we have one PHY in PCIe, one stack, and we expect the same silicon to interoperate across PCIe devices, other PCIe devices, we support multiple form factors. This is expected given that PCI Express is an ubiquitous interconnect across the entire compute continuum. We have to support a wide range of form factors which start with small devices, handheld, to industrial PCs, to the edge, to the data center. The form factors that are represented here is a subset, just to give a flavor. So we have things like a BGA. So these are soldered onto the board. The smallest footprint form factor is M.2. They range from 22 millimeter by 30 millimeter to 22 millimeter by 110 millimeter, typically used in SSDs, in boot slots, for data center storage, wireless WAN. We have U.2, which are widely deployed for SSDs with hot plug capabilities. Then we have the oldest and most popular card electromechanical form factor, CHEM for short, which comes in 4 flavors of height and length. And it has a wide range of power usage that the card can have. There is a robust compliance program. We also have SD Express, which is used in handheld, IoT, automotive. CF Express is used for high-end still and motion cameras. Then there is a set of enterprise and data center small form factor EDSFF that are used for, of course, enterprise and data center applications, primarily in the SSD space. So you got E1.S that's shown there, E1.L. Then there are a whole different flavors of E3, E3.S, E3.L, E3.S2T, E3.L2T, and they range in power from 25 watts to 70 watts. In addition, there are a lot of proprietary form factors. For example, HPC applications, they use multiple kilowatt worth of cards. So we expect same silicon, same spec, same PHY, right? Everything to support these wide range of multiple form factors because PCI Express is deployed in a wide range of systems in the compute continuum. Let's look into the evolution of PCI Express, the underlying interconnect technology driving different types of load store IO interconnect. PCI Express debuted with the release of PCIe 1.0 specification in 2003. We double the data rate every generation while maintaining full backward compatibility as shown in the table and the diagram on the right hand side. Since PCI Express has been evolving in a cost-effective, scalable, power-efficient, and fully backward compatible manner, it has become the ubiquitous I/O across the compute continuum. So you got PC, handheld, workstation, server, cloud, enterprise, HPC, embedded, and IoT, automotive, all of them using PCI Express. You have one stack, one silicon, but capable of working seamlessly on multiple form factors across these large set of usages. Different widths are there for different types of devices. We have by 1, by 2, by 4, by 8, by 16. Of course, different speeds like we see on the table there. Full backward compatibility ensures that a by 16 Gen 5 device interoperates with a by 1 Gen 1 device. We have multiple PCI Express devices that are at the leading edge of this transition. Networking, XPUs are some. Right now, we are working on the 6th generation of PCI Express specification. doubling the data rate again to 64 giga transfers per second using PAM4 signaling. We have made a lot of innovations with low latency FAC, Flipboard, etc. that results in better bandwidth efficiency while lowering latency, which is unprecedented. We have a webinar where we delve into the technical details of PCIe 6.2 approach that's publicly available if you are interested. Now my colleague Anil will walk through the application of PCIe to various IoT segments, starting with edge computing.
Thank you, Megan, and thank you, Debendra, for a nice overview of IoT applications and the evolution of PCI technology. Now, we will take a look at how the PCI technology can be applied to some of the edge use cases and some architectures enabling the IoT applications. So here we see an entire end-to-end system of IoT applications. On the left-hand side, we have devices and things which have less amount of compute in them, and some of them can operate locally, sense the environment, take an action based on the inputs from the environment, and control an actuator and close the loop. So essentially some kind of closed loop control or observing the environment. From there, to the right hand side, we have cloud computing, where large amounts of data can be processed using artificial intelligence, machine learning, deep learning, etc., and inferences can be made. But to transport all the data generated at the edge to the cloud, and processing there involves a lot of delay. So there is a need to process the data closer to the source, so that you can take you can take you can make better decisions quickly in a timely manner. That is essentially what edge computing means. It brings cloud computing capabilities to the place where the data is generated and makes decisions locally. So, and that way improves the latency, it brings determinism to the processing, and also improves security of the data. Now, let's look at how PCIe fits into this overall end-to-end edge computing paradigm. So here we see a edge computer or an edge gateway, and essentially there is a CPU of varying degrees of computing power is the core at the core of it. And The architectures are similar to what you find in cloud computing, but at a smaller scale. The key here is that the same type of architecture scales for smaller compute intensive applications to bigger compute intensive applications. So you can reuse the same design or the same architecture for different capabilities and for different levels of computing that you require for different vertical markets. What edge computing allows you to do is bring the capabilities to the cloud and deploy them broadly without in a very cost effective manner. So here what you see on the right hand side top is that you have two WAN connections. Essentially, IoT is an always on connection. People expect 100% availability. So having two WAN connections essentially allows us to make a failover in case of one of the connections are gone. Typically, satellite connections, wireless LTE connections, 5G connections provide the remote cloud connectivity. The fiber optic connections based on Ethernet provides wired connectivity. That at home, if you look at home deployments, you see DSL and cable as also WAN connectivity. So essentially all these modules can be connected to the CPU via a PCIe connection, which allows for high bandwidth, low latency, and deterministic data transfer from the WAN to the CPU. On the LAN side, on the left side, multiple wired or wireless LANs can be used to connect different devices in the local environment. In the retail environment, for example, you can connect your um, barcode scanners that people carry during in within the store wirelessly to the using wireless LAN like Wi-Fi to the gateway. If you are looking at smaller devices, temperature sensors, or light bulbs, etc., they can connect using Zigbee as well as Bluetooth protocols, and those modules also connect to the CPU via PCIe. Wired computers in the retail store can be connected via standard Ethernet LAN, gigabit LAN, or 10 gigabit LAN as the data rates require. So essentially, multiple wired and wireless LANs are there to provide local connectivity, whether it is in a factory, whether it is in a retail environment, or a medical facility, etc. And all these modules are typically brought over to the CPU over standard PCIe connections. Um, One of the applications of edge computing is to deploy artificial intelligence based on deep learning and machine learning, and specific hardware accelerators based on ASICs and FPGAs are widely deployed, where those computations can be done more efficiently on those accelerators compared to the CPU. And PCIe is essentially enabling heterogeneous computing applications for edge platforms. FPGAs are also typically used for these applications originally before the algorithms are not finalized. Once the algorithms are finalized, you can transfer them to dedicated accelerators ASICs. But if your algorithms keep changing for different verticals, or if you are still developing the algorithms, FPGAs are a good complement to that. Edge computing solutions also process large amounts of data. We need to store it, and NVM Express is a good choice for that. It allows data to be stored without the bottlenecks of SAS and DAS, etc. Uh, IO expansion is also an important capability of edge computing, because edge computing platforms in different verticals use different legacy connections. For example, in industrial automation, there are multiple industrial Ethernet protocols like EtherCAT, Ethernet IP, Profinet, etc. While they use physical layers based on Ethernet, their protocols are different. So for a computer to have different modules baked into it will make it more expensive. So different depending on the vertical applications, we can customize the modular computer using standard PCIe connections. So PCIe enables bringing in multiple IO standards over to the edge computer. For video acceleration, for example, video capture cards based on HDMI or MIPI can be connected to this computer also via PCIe. So this PCIe is kind of the core connectivity within the box for edge computers. We may find different connectivity for box to box connection, LAN connection, or WAN connections, but ultimately within the box, they all get translated to PCIe before it goes to the data processing accelerator or to the CPU. So, what are the key performance indicators for edge computers, and how PCIe contributes to that? Let's take a look at that. Latency and determinisms is very important for IoT applications, as Devendra mentioned earlier, because they are real-time applications. And if you have to finish a task, you have to finish it before, right at the deadline, not too much earlier or not too much later. So deterministic behavior of the system is important. Uh, and low latency communication between elements are also very important. Key applications are robotics, factory automation, industrial process control systems, video surveillance systems, etc. Load store low latency PCIe is a good candidate for enabling this. Bandwidth is also increasing. In old times, sensors had sent a few bytes of data every now and then. Nowadays, in autonomous cars, video surveillance systems, etc., a lot of data is being processed. For example, 80% of the internet traffic today is video traffic. People are doing cloud gaming. People are doing real-time analytics of the data. Uh, People are doing for transportation, etc. Most recently, one example is that during pandemic, when you go to an airport, your real-time images, both visual as well as thermal images, are being scanned, and if people are sick, they are being separated into a different line. So a lot of data has to be processed very quickly and very fast, and you have to store those data as well. And transporting all that data to the cloud for processing is very expensive, and PCIe with its DMA capabilities, etc., is a good standard for providing this solution, as we saw in the previous page. Uh, in addition to improving the latency and bandwidth, edge computers also enable you to store the data locally and within the same geography. You don't have to send it to a remote cloud provider whose data centers may be in another country, and the regulations there might be different. There are strict regulations on data privacy in Europe, for example, in GDPR regulation. So to make your systems compliant and broadly deployable across the world, edge computing is a key uh, new paradigm shift there. As I mentioned earlier, to enable AI, machine learning, and deep learning, acceleration services are also gaining momentum, and the modular edge computing architecture is a key element of that. Now let's look at the test equipment vertical market. Measurement accuracy is very important, whether it is semiconductor testing, automotive testing, or any other production or development testing environment. Whether you are measuring a voltage, whether you are measuring a temperature or a current or vibration, etc. Uh, PXI is an extension standard to PCIe, where you can have modular cards designed according to the standard plugged into a PCIe-based chassis. And you can start small with having a couple of cards, and as your test demand increases, or if your throughput demand increases, you can add more cards. This commercial use of adding cards from different vendors allow you to customize your test solution without having vendor lock-in. And as performance of the system and throughput demands increase, you can swap out old cards and replace them with the new cards with higher compute capabilities. And the connectivity is PCIe, and it is backward compatible, so you don't have to keep changing the chassis or throw out the entire rack, because your production test needs changed from last year to this year. So these type of solutions are getting wider adoption in the test market. One of the workhorses of industrial automation is the embedded PC. PC-based ecosystems have a large developer base. It's based on standard connectivity like PCIe, and they are produced. They are mass-produced, uh, reducing the cost. So adoption of those PCs for the harsh environment, whether it is in a mine, whether it is in a factory, or whether it is in the power distribution station, that is what is happening in the IoT market. So standard PC-based architectures are widely deployed for IoT applications. Uh, for example, SCADA systems in energy distribution, manufacturing execution systems in the factory, etc., can be run on standard software based on PCs. PCs also provide a lot of computing power. So in the past, if you used the different systems for doing application-specific solutions, now you have the opportunity to consolidate multiple workloads on the same system. So using standard-based PCs, you can replace multiple hardware boxes with one box. So that will save you a lot of real estate, that will save you a lot of power, that will save you a lot of maintenance cost, and also initial capital cost. Here we have an example of a manufacturing system where multiple computers used to be placed in this machine to do application specific solutions like a PLC, programmable logic controller, human machine interface, the camera and vision subsystem, and the motion control of the belt or moving the part throughout this machine. So using an industrial PC, you can consolidate those four systems onto one machine. And sometimes when you consolidate multiple workloads, you need to prevent interference from one workload with the other workload so that your system has no security violations, so your system behaves in a deterministic manner, etc. Virtualization is the key there, and it allows multiple workloads to coexist on the same hardware. PCI technology allows for virtualization and direct mapping of physical functions to virtual machines. So PCIe is an essential enabler for this kind of in the workload consolidated PCs and reducing the cost of ownership for the factory owners and other smart city owners and things like that. As we saw in the edge computing case, um, we saw in the edge computing case, multiple subsystems can be connected by PCIe. PCIe allows for I/O virtualization that improves determinism and security, and standard PCs can support Windows operating systems, Linux operating systems, or any other real-time operating system of your choice. In addition to this, newer improvements in the PCI standard for deterministic transfer of timing information from peripherals to the CPU, such as precision time measurement, improves the deterministic behavior for IoT systems that are safety critical, whether it is in automotive, whether it is in aerospace, whether it is in industrial automation, etc. PCIe also has multiple form factors. So industrial compute modules based on the PIC-MIC standards like COM-Express, a small form factor, and M.2 are widely used. So if there is a new computer that is available and that you want to deploy into an existing system, you can plug out the compute module and replace it with a modern module without changing any of the wiring or without designing a base carrier card or form factor of your chassis. So upgradability is what the multiple form factors bring to the market. Low power and fanless designs are also important for broad deployment of industrial PCs in external environment, not in an air-conditioned environment, maybe on the street side, maybe in a vending machine, etc. And PCIe being a low power interconnect contributes to that. Essentially, as I mentioned earlier, industrial PCs are scalable. There is massive ecosystem of software, and mostly you can use standard form factors, reducing the deployment time. Finally, there have been um, different, very many webinars on the applications of IoT in automotive, autonomous driving, etc. in this forum. But I want to touch here how PCI technology and its variants are being used in automotive today. Automotive systems, such as a typical autonomous car, generate a lot of data, like 4,000 gigabytes per day, each day. And then that can be coming from any one of the subsystems that you can see here, whether it is the tracking system by GPS, whether it is the LiDAR system that is directing the car, the radar systems and the cameras, the ADAS system, compute systems, the infotainment system, etc. Earlier, automotive interconnectivity used to be low data rate, like the CAN interface, which sends up to 1 or 2 megabits per second over a twisted pair. But the addition of all these high bandwidth sensors and the need for high compute for doing path calculation, etc., essentially need a lot more connectivity within the car itself. Also, the car needs to communicate with its environment, either using Wi-Fi type vehicle to infrastructure technologies or LTE and 5G connections. To address the increasing bandwidth needs, Ethernet has become a system to system connectivity within the car itself, and PCIe has become the connectivity of choice within the system to connect multiple CPU sockets, connect CPUs to accelerators, or to connect CPUs to networking devices for LTE, 5G, or Ethernet. Also, a lot of advanced navigations algorithms are being developed as we speak, and they are not finalized. So FPGAs are also being widely deployed in the automotive market. To the right hand side in blue, you can see an architecture where various peripherals um, in the car is connected, and a PCIe switching is used to connect them to the CPU as well as to the other peripherals. Um, so essentially, PCIe is enabling the automotive revolution for electric cars as well as autonomous cars. So we have looked at several use cases. We had a time only to look at a few select ones. Hopefully, you will have other ideas, and more use cases will emerge where PCIe can enable um, broader IoT deployment. With that, I pass the mic back to Devendra for walking us through a summary and defining some next steps.
Thanks, Anil. As we saw, PCI Express offers compelling value, right, for the various IoT segments. The value of an open ecosystem is that it offers plenty of devices that are out there. These devices can be your artificial intelligence devices, they can be machine learning devices, networking NIC kind of devices, storage and components, wireless connectivity, graphics, GPUs, display. And the beauty of that is that all of these, you just plug into any system, it just works. You don't have to worry about, do I have a Gen 1 device? Do I have a Gen 5 device? You plug it into a system, the whole open ecosystem and the plug and play model means that things just work. We looked into the rich feature set of PCI Express. We summarized it in the table here. And it demonstrates why PCI Express offers the right solution for the various IoT segments. We got seamless scaling of bandwidth with speed and width. We saw that, right? We go from everything from 2.5 gig to 5 gig to 8, 16, 32, now 64. So the speed evolution is going on. On the width side, we got everything from a by 1 to a by 16. So bandwidth can scale. The PCI Express protocol is very high efficiency. In other words, the overheads in terms of physical layer or the link layer and all those are fairly minimal. Right? We have shown in other places where that efficiency is really fairly high, can be anywhere from 60% to 95% efficiency. All of these, it ensures that you have a cost-effective and power-efficient performance CAGR, right? Compounded annual growth rate, while the latency remains flat. It's a low latency, it's a flat low latency, it doesn't change. You got direct memory access, direct load store semantics, and memory accesses typically are in the range of 100 nanoseconds to 500 nanoseconds. So low latency, high performance, high bandwidth with good bandwidth efficiency in a power efficient and cost effective manner. Those are what PCI Express brings to the table. Now this load store access model with direct memory access semantics, it ensures that all the components that you have, right, the ones that, for example, Anil walked us through, they can interact using shared memory for high performance. Uh, to give some example, PCI Express offers message counter capabilities. It offers compelling RAS with strong CRC, link level retry, which is really ultra reliable if you measure it in terms of the fit or failure in time, we get better than 10 to the power minus 8 failures in a billion hours, which is practically zero. And this is critical for functional safety. We guarantee determinism through accurate time stamping using, for example, the precision time measurement features. Basically, you pick any metric, be it your latency, be it the bandwidth, be it the power consumption, be it the low power states, be it ease of deployment or cost. PCI Express is simply the best interconnect available to the industry. And that's what happens when you got 800 plus member companies that are actively innovating. You just are going to get the best. It has a proven track record of constantly innovating to meet the needs of various segments in a proactive manner, right? We don't wait for things to happen. We are proactively looking for usages, and we are making sure that the spec evolves in a backward compatible manner to address that usage. And we do that while retaining the key characteristics like a single standard. We want to make sure it is high volume manufacturing. We don't want to go after something that is a niche. It has to be HBM friendly. It has to deliver power efficient performance across all the segments, right, of the compute continuum in a cost effective manner. As a result of all of this, PCI Express has a breadth in the technology ecosystem with the 800 plus member companies that is simply unsurpassed by any other technology. You can take a look into whether it is off the shelf IP blocks, whether it is the available components, whether it is the modules, or whether it is the widely deployed software base. We have it all. So other standards like Ethernet, MIPI, HDMI, CAN, USB, Thunderbolt, etc., they basically connect to the system or platform using a PCI Express bridge. And it's fine because those are solving different problems. So they need to coexist, and PCI Express provides that bridge to so that you can go off to those other things like, whether it is networking and things like that. PCI Express is not a networking protocol. So of course you need to have a networking connection. So you can do that using a PCI Express bridge. PCI Express is fundamentally at the heart of connectivity in any modern computing system. Specifically in the context of IoT, PCI Express offers the ease of transition from the IT world to the IoT applications. So it spans from off-the-shelf form factor, modular components, debug tools. Most important of all of this is that it has us all, the developers that have decades of experience starting from the PC world. So the PCI Express journey, it's an ongoing one. We have 2 decades and 6 generations under our belt. I'm sure that I speak for everyone here when I say that we are looking forward for continued innovation for decades to come. It's something good that has happened, so we are going to continue on this journey. Consider joining PCI SIG if you have not done so, and be part of that leading edge of innovations in the compute continuum. I always say the journey could continue. The journey it's an ongoing journey. It never ends. It keeps on going on and on and on. Thank you all for joining. Now let us take the questions.
Great. Thank you, Debendra. Thank you, Anil. The first question here is, it seems that the IoT segment spans many different capabilities. Are we better off with a common standard like PCIe, or should we consider different standards for different capabilities?
Okay, so Megan, that's a great question, and it's very true. IoT covers different types of verticals, and we need different connectivity standards. For example, even within wireless connectivity, we can have um, Bluetooth for you know uh, very low ranges. We can have Wi-Fi for local area connectivity. We can have cellular IoT for low bandwidth, high distance connectivity. We can have broadband cellular connectivity and anything from LTE to 5G, from 3G, right? However, as Devendra just mentioned, when all this connectivity comes to a gateway or to the computing element where the decision is made, all these networking protocols need to transport data to the CPU or the processing unit, and PCIe often becomes the connectivity standard. If you look in the market for wireless modules, whether they are LTE modules, Wi-Fi modules, Zigbee modules, 802.15 based other standards, Bluetooth modules, etc. The backend connectivity is PCIe. So PCIe is not going to replace those networking protocols, but PCIe is going to connect those protocols over to the computing element and will stay as the connectivity standard within the box. So they tend to coexist, and one is enhancing the other. And as the data capabilities of PCIe go up, that enables higher bandwidth Ethernet, higher bandwidth LTE, and 5G modules to be connected to a CPU. Hopefully that answered the question.
Great. The next question here is, will a new dedicated form factor be introduced for IoT?
I can take that one. We support BGA, M.2, and as we saw, we support a wide range of form factors. And normally, the way form factors work is anytime there is a usage, people go ahead and introduce a form factor. And that's the beauty of the PCI Express, right? The silicon is there, both sides will work irrespective of the form factors. Of course, you need to make sure that you do all the pin placement and everything appropriately. That's the job of the form factor. But yes, anytime there is a specific IoT usage that is not being, or an evolving usage, right, that's not being served by the host of the form factors, innovations will happen. It has happened in the past. That's the reason why PCI Express does not have, uh, you know, 4 or 5 form factors. It has quite a few form factors, right? So yes, PCI as a technology is very open to form factors. With that, Anil, did you want to add anything?
Thank you, Devendra. That's a great answer and a great question as well. So, as you said, it is going to be the market forces and the vertical application demands that are going to drive new form factors. If you look at one of the most recent development is that automotive computing units, they used to be single board computers, but due to the heavy demand of computing requirements for autonomous driving, you can see PCIe blade-based systems being the heart of the brains of the ADAS systems today. So essentially, the use cases and the usage demands are going to drive new form factors, and we hope to continue to see those evolutions.
Great. The next question here, how is the host ecosystem gearing up to support PCIe technology-based SSD card or SD cards? When can we expect products in the market?
We already have products there, like those include things like SSD, CF Express for cameras. So that that's already out there, and definitely expecting to see more and more of those going forward. But those are already there. In fact, I quickly looked up day before yesterday for some SD cards, and yes, those are available. Did you want to add anything on it?
But no, that I don't want to add anything further because a lot of SD card capture cards are based on SD interface to the right side and then PCIe to the CPU side. They are available at the market today. Yes.
Does PCIe technology work with functional safety standards, since many applications you cited, like industrial robotics and autonomous driving use cases, require these high levels of safety?
Yeah, Devendra, I will start and then you can add to any further
Sure.
insights. Essentially, whether it is robotics or avionics or autonomous driving, you know, the machine should not hurt people, and functional safety is essential. We can do it at the silicon level, we can do it at the interface level, we can do it at the software level, and we can also do it at the system level by providing multiple redundant system, and PCIe standards actually cater to that at each of those levels. So PCIe IP used for essentially for this kind of ASICs and SoCs for IoT essentially will have to have a debug capabilities, self-test capabilities, error correction capabilities, etc. that are defined by the system. And so essentially it is a stacked approach. You cannot do everything in the silicon. You have to do it at every level, and PCIe caters to that today. And essentially, when you make choices along the system design, all the way from hardware to software, you have to make the right choices for the entire system to be reaching the desired level of safety that is specified by the regulatory body or the industry association.
That's great. I think you answered it. Let's go to the next one, Meg.
Next question is, how important are CMA, component measurement and authentication, and IDE, integrity and data encryption in these environments?
So let me start with this one. They're very, very, very important, right? As we rely more on these computing to control different aspects of our lives, right? Whether it is industrial production to autonomous driving, we need to make sure that we are doing things in a safe manner, right? And we are doing things where somebody cannot hack into your system and cause harm. So we do expect to see these technologies that PCI Express has been widely deployed in order to make security a topmost priority for us. And we do see a lot of applications in the IoT space and in the autonomous driving kind of space. Anil, did you want to add anything?
Yeah, besides that, Devendra, also, we need to encrypt the data, and newer PCI standards are coming about end-to-end encryption within PCIe, right? Last year, there are new initiatives in the PCI sec to define those things, whether they are used for industrial automation or autonomous driving, etc. So encryption is also becoming important. And while we encrypt data, we still need to maintain that we still maintain low latency as well as deterministic behavior of the interface. So that is the challenge we have.
Today
And by the way,
we
if I want to add something, security is like it's not a, you did something and you are done. It's a constant evolution, right? So as new threat models emerge, that's uh, part of the PCI Express value, right? We constantly monitor for those threat models, and we make sure that IO technology that we are driving is keeping up, right? It's being proactively looking out for those new threat models and addressing those. And by the way, we also work very closely with other industry bodies to make sure that users have a seamless experience, right? So so we work through, even for the development of the CMA and IDE specification, it was done with keeping in mind other IO standards so that people can deploy this and have a good user experience. But it's a ongoing journey like anything else. Next question, Meera.
Next question here. Today you were discussing many feature-rich, high-performance IoT devices. There's no doubt that PCIe technology fits these. Can you tell me a little bit more about the situation of adaptation of PCIe to low-power endpoint IoT devices?
So let me start with this, and Anil, you can take over from there. PCI Express from a let's split the low power into two categories, and those are like both sides of the same coin, right? One of them is effectively the power consumption while delivering bandwidth as measured in picojoule per bit, right? So this is when I need to run full steam. How much power am I consuming? I really have a need to transfer the data. Second aspect of it has to deal with the low power capabilities. For example, when I'm not uh, transferring as much data, or I'm not transferring any data at all, what do I have? So in the first case, if you look into the what we call the maximum bandwidth case, right, where you need every possible or you need substantial percentage of the bandwidth that your interconnect offers. PCI Express has got I've done this analysis several times. PCI Express has got the best picojoule per bit in the industry, and it's not it's a simple outcome of if so many people do the design, right? I mean, they're going to scrape every picojoule out, every sub picojoule, right, out of their design and give you the best design that's possible. It's just good engineering. The second part, which is a lot more challenging, is how do you make sure that your specification, by the way, no, the specification does allow for those low power in terms of picojoule per bit. If you look into even things like Gen 6, right, we did very low latency FEC, we did a bunch of those things to make sure that designs can still be really, really low power, right? We made a bunch of trade-offs, right set of engineering trade-offs to get there. If you look into the aspect of low power kind of support, we did things like L1 substrates, right? So with L1 substrates, when you can get to microwatts of power, which is what you need for handheld devices, right? When the device is idle, you really don't want it to be consuming power; it's just sleeping, right? But you want to wake it up very quickly so that you can do any kind of transfer. We are also introducing this notion of L0P because if you look into the L1 or L1 substrates is no data movement at all. The full-blown L0 is full data movement. What we figured out is that and we had solutions for the ones in between, but those had higher entry and exit latency. So we are addressing that with L0P with Gen 6. And again, we did discuss that in the 6.0 webinar, so you can take a look into that. So basically, we are, from a specification point of view, we are going at power consumption in a very systematic manner, and we are committed to delivering the best user experience there. And that does include things like IoT, which are very low power devices. Same thing with the handheld. Uh, Anil, did you want to add anything?
Devendra, you are right. So when we have large amounts of data to be transported and still save power, PCI is a great interface. And as you mentioned at the beginning of the answer, if you are looking at the very low amount of data to be transferred very infrequently, like condition monitoring in a farm or something where you are looking for the humidity once in a day, then PCIe is not a good choice there. So it really depends on the use case, and more and more low power devices are being uh, deployed based on PCIe, and it is penetrating the market.
Great. And with that, I think we'll go ahead and wrap up for today. So we just wanted to thank you all so much for joining today's PCI SIG webinar. Uh, as a note too, more information on this topic can be found in a recently published contributed article by Devendra and Anil that's in Electronic Design. Uh, as a note too, I know that there were some questions that we weren't able to get to today, so any unanswered questions we'll plan to develop a blog that will be on the PCI SIG website that you all can reference later on. So thank you again to Devendra and Anil for your time today, and thank you everybody who was able to join.
Thank you all, and stay safe.
Thank you and have a great day.